And that collision, I mean, I think it goes without saying, but if the forces are equal and opposite, then the amount of time is going to be the same. You can't be in contact with an object longer or shorter than the object is in contact with you. As soon as you're no longer in contact with the object, it's no longer in contact with you. I think that's fairly straightforward, I would hope. And so what that means is the impulses, your change in momentums or your F net times time, must be equal and opposite. Which leads us to kind of a rather interesting result. This idea leads us to something called the law of conservation of momentum. Now, in physics, conservation laws, the law of conservation of whatever, these conservation laws are awesome. There's a bunch of them. They're wildly important. And so this is the first one that we've talked about. We're going to talk about another one next chapter. But this one, the law of conservation of momentum, says that, grab a different color, in a closed system, or in an isolated system, momentum is not created or destroyed. What that means is for an object that's just hanging out, it will not spontaneously start moving or just all of a sudden stop unless something else is acting on it. So momentum is not created or destroyed, only transferred. During interactions. So two objects need to interact with each other in a particular way for the momentum to change, is what this is saying. An isolated system is any system where no outside forces are acting. So the law of conservation of momentum is going to lead us to three kind of interesting scenarios. Because of this, in an isolated system, momentum is not created or destroyed. What that means is the sum of all of your momentum at the beginning. So that, remember, that symbol there is a mathematical symbol. It's a Greek letter sigma. It means the sum. Just like we had the sum of the forces, this is the sum of the momentums. And that I stands for initially or at the beginning. The sum of your momentums to start must equal the sum of your momentums at the end for all objects in the system. Which is going to lead us to kind of a ridiculous expression, but I'll write it out like this. You're going to have your first object has a mass. It also has some sort of initial velocity. So I'm going to write this as m1v1i. So the initial velocity times the mass of your first object is the initial momentum of object 1 plus m2v2i, the initial momentum for your second object, plus plus mx/vxi, where x is just the last object, your xth object. So the sum of all your initial momentums must be equal to, and we need the space over here, so let's use it a little bit better. M1 V1 final plus M2 V2 final plus ... plus mx vx final. So we're going to take all of the initial momentums for all of the objects in the problem, and the sum of those needs to equal the sum of all of the final momentums for the final objects in whatever the system is. So momentum itself, not a difficult concept, mass times velocity. This is where momentum gets really interesting. And we're going to look at three styles of problems in one dimension. Yes, one dimension. One dimension? Yes, one dimension. These are all going to be 1D problems in grade 11. But momentum is a vector. So in vectors, as you've seen with inclines, as you saw with projectiles, we can break vectors up into multiple directions. We had 2D projectiles when I was launching things up at an angle. The inclines gave us two-dimensional styles of problems. These momentums are only going to be one-dimensional because we haven't looked at adding vectors together. We're going to save that to 12. So we're looking at one-dimensional momentum problems. There are three styles. Stop me at any point if you need to write something down or if I'm going too quick. Here we go. The first style we're going to look at is what's called an elastic collision. I want a different color. I want this color. Oh, that one's dead. Oh, this one. Let's go with brown. Here we go. The first style of collision is what's called an elastic collision, and an elastic collision is defined as a collision where objects do not stick to each other. Any collision where they don't stick, we're going to define it as an elastic collision. We're going to refine this definition when we get to energy in the next chapter, but for now, that's what we're going to call it. A 7.1 kilogram bowling ball is rolling to the right at 3.8 meters per second when it collides with a stationary 0.4 kilogram bowling pin. After the collision, the bowling pin is traveling at 2.9 meters per second to the right. So it's in the same direction, but it has slowed down, which you would expect it to. Not a lot. We want to know how fast the pin is moving after the collision. So there is no other way to analyze this kind of problem other than looking at the relative momentums of the situation. So here's what we've got. We've got a scenario where we have a before setup and after setup. And we're going to draw an arrow in between. The arrow in between is where the collision happens. There's a point in time in the middle. So we've got a bowling ball. There's our bowling ball. It's traveling to the right. So let's give it some speed lines. And we've got a bowling pin. Let's try this guy here. So here's my attempt at drawing a bowling pin. The bowling pins always have that thing on the neck. Here's my bowling pin. The bowling pin is not moving. If you've never bowled before, the pins are stationary. It'd be way more interesting if the pins were moving. Afterwards, the after scenario, you've got a ball that is still moving to the right, and now you've got a pin. That was terrible. Yep. We don't necessarily know which way the pin is moving, but you can make some assumptions. What's the only direction that makes sense for this pin to move? To the right? to the right as well. So let's toss some speed lines in there. And now we're going to go see if we're right. We want to call, remember, momentums are vectors because they're based on velocity. Velocity is also a vector. So we want to call a particular direction positive. So let's call to the right positive. And we'll see if we're right. If we find that this velocity for the pin ends up negative, that means that somehow the pin is moving backwards, like to the left, which would be weird. If you were bowling and the pin shot backwards at you after you hit it with a ball, that would be weird. So let's try it. We're going to set up everything we know here. We know that the velocity of object 1 initially is equal to 3.8 meters per second. And we know that the mass of object 1 is 7.1 kilograms. When you bowl, the ball does not change after the collision has occurred. So M1 afterwards is going to be the same 7.1 kilograms. But now we've got a different final velocity. We're told it's still to the right, but now it's 2.9 meters per second. So it has slowed down, which you would expect it to do. And now we've got the bowling pin. Initially, so the velocity of object 2 initially is equal to 0. And its mass, the mass of object 2 is 0.4 kilograms. Presumably the pin is still intact, so the mass of object 2 hasn't changed. It's still 0.4 kilograms. But now it has some final velocity, and this is what we're looking for. And you need to do this for every object in the problem. Like if you were extreme bowling, for example, where some ridiculous game where people are bowling at the same pins from opposite directions, that'd be fun, right? If we'd have another ball coming in here to the right and they all hit at the same time, you'd have another object that we'd have to deal with. But right now, bowling, standard bowling, we only have 2. So let's set this thing up. This is your starting equation for conservation of momentum. It's just like Newton's second law. Every Newton's second law problem starts with F net equals ma. Every conservation of momentum problem starts with the sum of the momentums initially equal the sum of the momentums at the end. So we're going to have m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. The sum of the momentums initially have to equal the sum of the momentums at the end. And the beauty of this is that because v2 initial is equal to 0, this term is gone. Because of this. So now we can plug in everything else we know. We're going to have 7.1 times 3.8 is going to equal, because plus 0 means the thing's gone, 7.1 times 2.9 plus 0.4 v2 final. And this is what we're trying to solve for. So to isolate v2 final, the algebra is sometimes the trickiest part. This expression here is positive, the 7.1 times 2.9. So I'm going to add it to the other side. We're going to get subtract it to the other side. 7.1 times 3.8 minus 7.1 times 2.9. And I'm going to divide that whole thing by 0.4. And that's going to equal v2 final. Now when you plug this thing into your calculator, you need to be careful how you do it. If you plug it all in one shot, you need to throw an extra set of brackets around your numerator. So your expression is going to end up looking like this. If you plug it in your calculator in one shot, it's going to become bracket 7.1, bracket 3.8, close that bracket, minus 7.1, bracket 2.9, close that bracket, close the first bracket we opened, And we're going to divide that whole thing by the mass of the bowling pin. Boom. So the bowling pin is moving at effectively 16 meters per second, which makes sense. It's a much lighter object getting hit by a much larger object. You'd expect it to move off quick. Maybe not this quick, but you'd expect it. That's why they have the thing at the back to catch all these pins, because the pins are flying up. Questions about how I tackled it? Yeah, heard it. Louder, please. Yeah, well, I'm going to do the second example. Or you wait for 2 minutes? I don't know if I can wait for 2 minutes, but I can wait for a little bit. Well, here it is ready. I'll talk about the second question. In the second one, we're going to look at I'll read it to you and you can tell me what the difference is. A 0.25 kilogram cue ball is traveling east at 4.5 meters per second when it collides head on with a 0.25 kilogram 8 ball traveling west at 5 meters per second. After the collision, the cue ball is traveling west at 2 meters per second. What is the final velocity of the 8 ball? How is this question different than the one we just looked at? There's two moving objects. So I don't know if you've ever played. So a cue ball implies that we're looking at a pool table. Normally when you play a normal pool, only the white ball is moving, at least initially, and then it hits the other balls and the other balls move then afterwards, after the collision. If you were like my cousins and I, what we used to do is we would play this psychotic game where there was one person on every corner of the table, and we would just take balls and we would just whip them. We were trying to throw the balls into the corner pockets, while other people were throwing other balls trying to reach their corner pockets. So you'd have collisions all over the place, and you'd have fingers getting smashed, and it was great. So it's one of these kinds of scenarios where you have multiple balls moving on a pool table at the same time. So this is a fundamentally different kind of problem. This one had one object stationary. This one does not. So let's draw it out. We've got a cue ball. The cue ball is white. I'm not going to color that in. It's traveling east. So let's throw some speed lines heading that way. The mass of object 1 is 0.25. The velocity of object 1 initially is 4.5 meters per second, and that's in kilograms. I've got a 8 ball. For those of you who have never played pool before, the 8 ball is black. So let's use black. And what's the 8 ball doing? Well, the 8 ball has a mass of object 2. It's the same mass, 0.25. V2 initial is going to be equal to, it's traveling west at 5 meters per second. Momentums are vectors. This one's traveling east, and by putting this one positive, what am I implying? The other one's going to have to be negative. They're traveling in opposite directions. We need to deal with that appropriately. So I'm just going to go in here into my diagram, and I'm going to say east is explicitly positive. So now if I've got V2 initial, that velocity is traveling west, so now I have to put a negative 5 meters per second in there. Some speed lines saying that this thing is definitely traveling west. So they're going to interact with each other. After the collision, there's our collision. After the collision, we've got a cue ball traveling west. So the white ball turns around and goes the other way. Its mass presumably has not changed. Its velocity now, velocity of 1 finally, is the cue ball is traveling west at 2. So if this thing's going 2 to the west, I have to make it negative. And the 8 ball is now moving a different direction. Well, we don't know that. The 8 ball is now moving differently than it was before. its mass, mass 2, is equal to 0.25. We want to know what the final velocity of the 8 ball was. So V2 final equals question mark. What does your gut tell you? If you had to guess, which way would you guess that the black ball is now moving? So east, that's what your gut says. Let's test it. Okay, let's put some speed lines to the east. We'll put a question mark above it. We don't know which way it's moving. If the final velocity here ends up positive, we said east was positive. If this velocity is positive, Lena's right, object's moving to the east. But if this shows up to be negative, somehow this object is still moving to the left or west. So let's ram this through our momentum equation. The sum of the momentums initially are going to equal the sum of the momentums at the end. So M1 V1 initial plus M2 V2 initial, they're going to equal M1 V1 final plus M2 V2 final. And this time, no masses are zero, no velocities are zero, so we can't cancel anything out. We've got all of this to deal with. So let's plug it all in. I'm going to 0.25 times 4.5 plus 0.25 times negative 5 is going to equal 0.25 times negative 2 plus 0.25 V2 final. So if you take a look at what happens here, I still want to isolate for V2 final just like I wanted to do over here. So to isolate for V2 final, I want to get rid of everything that's on the same side of the equal sign as V2 final. So the first thing we're going to do is get rid of any term that doesn't include it. That'd be this guy right here. Now, this thing here is negative. The 0.25 times negative 2 is negative, so I'm going to add it to the other side. So this is going to become 0.25 times 4.5 plus 0.25 times negative 5 plus 0.25 times positive 2 now. It was negative, and I added it over to the other side. If I divide this whole thing by 0.25, this is going to equal V2 final. Now you could ram this through your calculator. Make sure you throw brackets around the numerator, but there's a cool little shortcut here. Does anyone see the cool little algebra shortcut before you just ram that thing through a calculator? Here it is. Because 0.25 is in every term in the numerator, and it's what you're dividing by, you can cancel it. Only because it's in every term. So boom, 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 boom. The masses are all the same, therefore they cancel. Beautiful. So then V2 final is just going to be 4.5 minus 5 plus 2. 4.5 minus 5 is negative 0.5. Plus 2 is positive 1.5. And it is overtly positive. So which way is the ball moving? The black ball. This result is positive. So was Lena right? She said the thing was moving east. East was positive. That's positive. She was right. Keeping track of your positives and negatives is really important. Comments, questions, concerns? Okay, that is elastic collisions. When you're ready, flip the page. Let's look at inelastic collisions. Inelastic collisions are where objects stick together. Elastic, they do not stick. Inelastic, they do stick. Examples of sticking objects look like this. You've got a 0.105 kilogram hockey puck moving at 48 meters per second, and it is caught by a 75 kilogram goalie at rest. If the ice is frictionless, at what velocity will the goalie slide on the ice after catching the puck? So for those of you who watch hockey, this is not normal hockey. This is, because normally in hockey, the goalie would have, skates, he'd be planted, they're making catches and they're not moving. In this particular example, goalie would have to be standing, skates straight, and he's taking the slap shot like a bat catcher. Puck's going to hit him. Presumably for a stationary object on a frictionless surface, I get hit with an object, what would you, and I catch the object, you would expect me to start sliding backwards. Conceptually, that makes sense, right? Cool, try this. You're standing on ice and I throw a football at you. You catch the football, the football can hit you. It makes sense that that object would cause you to slide backwards. Assuming you're not bracing yourself, I think that's conceptually, you're not responding, so I'm hoping you're following. Let's try this. So that's what's happening here. We've got a puck being shot at a goalie. So presumably, I'm drawing this on the left-hand side of my page. So the puck's going to be moving this way. We've got a goalie here. Goalie's got fat pads. And a glove. This is not to scale. The puck is huge. But this is the scenario. Puck moving its stationary goalie. I'm going to call to the right positive. Because that's the only thing that makes sense here. The puck's moving to the right, and presumably this goalie, who will then catch the puck, it only makes sense for that guy to slide backwards. The only other option is he doesn't move, which we're going to find out what that is. So either V is going to be 0 or V is going to be positive. If V shows up negative here, that means goalie got hit with the puck and is now moving towards where the puck came from. Doesn't make sense. For an inelastic collision, or when the objects have stuck together, there is a specific change we're going to have to address here. So I have two objects to start, M1 and then V1 initial. M1 is going to be 0.105. The velocity is going to be 48 meters per, that's in kilograms. And the velocity is in 48 meters per second. The goalie, that's our M2, is going to equal 75 kilograms. And the velocity of our goalie initially is 0. We're told our goalie is at rest. At the end of the problem, how many objects do we have? Here they wake up. How many distinct objects are there in the second part of the problem? Sorry? You have no clue. All I wanted you to do is wake up. You didn't have to answer the problem necessarily. Well, you've got a goalie that now is holding on to the puck. For all intents and purposes, you've got one big object that is larger than bigger than either of the two objects that came before. So now over here, we've got one mass. I'm going to call this the mass of 1 plus 2, because when objects stick together, you're going to add those masses together. The mass of the system now, or the puck and goalie together, is the sum of their individual masses, because they're sticking together. It's going to be 75.105 kilograms. And we want to figure out V of 1 plus 2 is what? That's what we're looking for. When the objects stick together, add their masses together. So the sum of the momentums initially are still going to equal the sum of the momentums at the end. At the beginning, I've got M1 V1 initial plus M2 V2 initial. And that's going to equal M of 1 plus 2 times V of 1 plus 2. The beauty of this is because the goalie wasn't moving to start, that is 0. So this is going to be 0.105 times 48 is going to equal 75.105 V of 1 plus 2. So substantially easier to solve. I'm just going to divide both sides by 75.105. And you're going to get that your velocity is V of 1 plus 2 is going to equal 0.067 meters per second. So slow, but not imperceptibly slow, because 0.067 meters per second is basically 7 centimeters per second. Moving backwards like this. Which you'd expect. Tiny object shot at a large object at 48 meters per second is going to cause the combined system, it's going to move, but it's going to be slow. And that's it. Another example. Do I want you guys to do this one? I'll take it ahead. There we go. We got time. A 35-gram bullet strikes a 5-kilogram stationary wooden block and embeds itself in the block. The block and the bullet move off together at 8.6 meters per second. What was the original velocity of the bullet? So this is another classic example of these collision kinds of problems. You've got a bullet being shot at a wooden block because we don't shoot things other than wooden blocks in physics class, unless you want to make it really interesting. The block and the bullet gets embedded in the block, and they move off together. So here's your situation. You've got a stationary block and a bullet. The bullet is moving at the block, and after they collide, you've got a situation where the bullet is embedded in the block, and they slide off together. For those of you who have never shot a wooden object before, we're going to assume that the wood just deformed around the bullet. The bullet is entirely encased inside that wooden block, and there's no splinters went flying off. If splinters go flying off, then the mass has changed, and at this point, we're not going to deal with that. So the bullet has been completely absorbed by the wooden block, and no pieces are missing. So let's set this thing up. I've got M1 V1 initial. Oops, I'm going too soon. M1 equals V1 initial equals. The mass of object 1 is 35 grams. When you're dealing with momentum, masses always need to be in kilograms. Velocities always need to be in meters per second. So what's 35 grams in kilograms? I'm going to take that value and divide it by what? There's 1,000 grams in a kilogram. So this is going to be 0.035 kilograms. And this is what we're looking for. We want to find the original velocity of the bullet. That is our unknown right there. Over here, we've got M2 and V2 initial. V2 initial is 0 because it's stationary, and the mass of that thing is 5 kilograms. After they interact with each other, M of 1 plus 2 is going to be the sum of the two masses because they're embedded. So it's going to be 5.035. And we know that the velocity of 1 plus 2 is going to be, we're told, they move off together at 8.6 meters per second. This is in kilograms. Bless you. So now we've got sum of the momentums initial equal to sum of the momentums at the end. And initial velocity of the bullet is what we're looking for. This, I'm going to get m1 v1 initial plus m2 v2 initial is going to equal m1 plus 2 times v1 plus 2. Now I can fill this thing in because this is 0, that is 0. So we're going to get 0.035 v1 initial. It's going to equal 5.035 times 8.6. So V1 initial is going to equal what? What would the initial velocity of the bullet have to be to cause the combined to move off at 8.6 meters per second? What's that value? Boy. Anybody? Do you have a number? How fast does that thing have to move? After you tell me how fast the thing moves. 1,237 meters per second. That thing is moving. And a 35-gram bullet is a big bullet. That is not your standard hunting round. That is a much larger round. Okay, yes, here today you may use the washroom. One last style of problem, then I will free you to play. Elastic collisions are where they bounce. Inelastic collisions are where they stick. An explosion is my most favorite kind of problem. I will do one of these, and there's a few different examples of them. I'm going to do one, and then I'll leave the other one for you to play with. So the one I'm going to do is the one on the right. You've got a firecracker sitting inside of a 7-kilogram pumpkin. I did something similar when I was teaching at a different high school a couple years ago, well, like 12 years ago. Rather than a firecracker and a pumpkin, I took a slab of sodium and I shoved it inside a watermelon. The thing exploded, because for those of you who are not aware, sodium reacts violently with water, and a watermelon is by definition full of water. So when Halloween just happened, so we have a firecracker sitting inside of a 7-kilogram pumpkin. Let's have some fun with our drawing, shall we? We've got a pumpkin. Pumpkins look sort of like this. This kind of looks like a peanut. There's my pumpkin. It's Halloween, so let's give him a face. Pretend my daughter carved this one, which means it's going to look terrible. There's our pumpkin. And we put it on the porch. And one of our neighbor children, or me when I was in high school, decides to be hilarious, grab the pumpkin, and put a firecracker inside. Grab the pumpkin, put the firecracker inside, you light that thing up, thing goes boom. And because this is only a one-dimensional problem, the pieces of pumpkin can only go in two directions. Because as soon as the pumpkin travels in more than two directions, it becomes a lot more difficult to deal with, which you'll look at next year. So, stationary object, firecracker goes off, boom, pumpkin's gonna split. And because you guys are only, doing physics 11, it's gonna move off in two directions. It looks like this. We're gonna rip the thing. Pumpkin gets torn in two. One of these things moves left, the other one moves right. And we're told a few things. The pumpkin was 7.5 kilograms. After it explodes, the pumpkin splits into two chunks. A 5-kilogram piece travels west at 10 meters per second. What is the mass and velocity of the other piece? Ignore the mass and velocity of the firecracker. It's negligible. Compared to the mass of the pumpkin, the firework is very small. So, here's the problem. You've got the before and you've got the after. At the beginning, the mass of object 1, the pumpkin, and the velocity of the pumpkin, I'm just going to call it M1 and V1 initial. The mass was 7 kilograms, and it wasn't moving. Afterwards, we have two pieces. So I'm going to call this M2 and M3. V2 and V3. We're told that we've got a 5-kilogram piece traveling west. So which of these pieces is that? Typically, when we draw these things, west is left. So this guy has a mass of 5 kilograms. We're told it's traveling at 10 meters per second west. The one thing we haven't done yet is because we're dealing with vectors here, we need to define a direction to be positive. Which direction do you want to be positive? East, you want positive? So if that's positive, then we have to take this velocity and make it negative. Keeping track of minus signs is the most common mistakes students make on this stuff. So if you're aware of that, keep track of your minus signs, you'll be fine. So if this is 5 kilograms, what's the mass of the other half of the pumpkin? Well, it's not half, but the other piece of pumpkin. It's 2 kilograms. We're assuming it's a clean break, that we haven't lost anything. And we want to find out what the velocity of that piece is. So it starts the exact same way. The momentum initially has to equal the momentum at the end. Initially, you've only got one object, M1, V1, and that's going to equal M2, V2 plus M3, V3. But because the object wasn't moving to start, this is 0. So you're going to have 0 on the left-hand side. You actually have to put the 0 in there. Equals 5 times negative 10 plus 2 times V3. So 5 times negative 10 is negative 50, and I want to isolate for V3. So because this is negative, I'm going to add it over to the other side. I'm going to get 50 equals 2 times V3. The math is nice and easy here because I cook the numbers to be easy here. Divide both sides by the mass of the other piece of pumpkin, and you get that if this chunk moves left at -10 or moves left at 10 meters per second, this lighter piece actually has to move to the right at 25 meters per second. That was quite the explosive. You've accelerated a 2 kilogram piece of pumpkin to right around 100 kilometers per hour, which is pretty wild. There it is. Who are you looking for?
I just have concerns with Alexis.
I don't know, Alexis, do you want to go with her?
She doesn't have to go anywhere.
You can have her.
I just want to check something.
And that's it. We blew up a pumpkin. And that's all I got for you today. This is the end of momentum. Looking at different kinds of interactions between objects, either the stickless collisions, the sticky collisions, or the explosions. I'm going to leave this one. I want you to try this one first. This one's going to be part of your homework. You've got a bullet sitting inside a gun. You pull the trigger, shoots the bullet. The bullet leaves the gun at 275 meters per second. What is the recoil velocity of the gun? I want you to try this one. I'll give you the answer. You're looking for a velocity right around -2.8 meters per second. So for those of you who've never shot a gun, you have a gun that was stationary. Now it's moving back into you at almost 3 meters per second. Shooting a gun is not a painless experience. So I want you to try it, see if you can get this result. And you've got you just arrived right around half an hour. There's 8 questions here I want you to take a look at. I want you to do all of them. There you go. So you got 9 questions and a half hour to do them. Good luck. Okay. Everyone who's playing games on your phone, put your phones away. You have a test on this stuff on Thursday. So get this done. Then you're reviewing. You finish all those things, you can hop on your devices.